I'm sure that you all know how to take the areas of some basic shapes like the triangle and the square, as well as know how to take the volumes of basic solids such as uh, cones and cubes. But there's another type of solid, one that's frequently found throughout calculus, and that is the volume of a solid of a revolution. Let's say that I take this curve that's bounded by x equals a to the left and x equals b to the right. And this curve has the equation of y equals a function of x. Then if I rotated this curve around the x-axis so that the solid that it formed would look something like this. Then how would we take the volume of this? First, let's look back at the proofs of uh, formulae for volume for some of the more basic shapes, such as the cylinder. So if we took a cylinder here, it's supposed to be a cylinder, and then we created the walls like this, then how would we find what the volume of this could be? Well, a cylinder is made up of, or we can think of it as, several stacks of circles. And then the amount of circles that the cylinder contains varies with the height h. So then I'll use a different color here. If we took this circle, which has an area of pi r squared, so pi r squared as its area, and then we integrated it, so we took the integral from height 0 to height h, so from here, the height is 0 to h, of pi r squared dh, then we would get that the formula for the volume of the cylinder would be pi r squared h. Because this is in terms of h and not r, then we could just factor this out of the integral itself, and then we would be left with a 1 in here, and the integral of 1 with respect to dh is just h, because 0 will just cancel out. So it's pi r squared h, by assuming that a cylinder is just a stack of circles. But could we use a cylinder here? Let's say that we took some arbitrary 2 points in this solid that we made. So these points could be here and here, but they have to be very, very close together. So let's say that we drew these two lines here, like so. And the width of this we'll call for, because this is basically a cylinder, but tipped on its side, we can call this the height, or h. And then if we assume that this is a cylinder, then this should therefore be the radius. And what is the radius? The radius, this isn't a perfect cylinder because this curve is going like this, which means that if I look at the cylinder from here, then it will have a different radius than if I look at it from here. So if I call this h, then what this is going to be here is that if I decide to call this coordinate x, and I decided to call this coordinate x2, then if I look at it from the side of x, then the radius that I would find could be considered y. And if I look at it from this side, then the radius would be considered y2. But let's say that we looked, instead of looking at just this portion, we looked at this whole section. This is far from being a cylinder because you can see that even here, the height transforms dramatically to become much higher here than here. But look to see that as you decrease the width of this, or really the height because it's a cylinder on its side, then it becomes more and more like a cylinder until the point where if I made an incision here and then I took the smallest possible number, I mean, we know that there's no such number, but if we took a very extremely small, infinitesimally small number and we moved it over one to the right, then it would be able to create a perfect cylinder, because if we're decreasing this to 0, or the height to 0, then we should be able to come up with a perfect cylinder, because we're getting closer and closer to being able to have similar heights. So then we can write this as a limit. So the limit as the height approaches 0 of what? So if we looked here, we managed to get the volume of the cylinder by looking at pi r squared, which is the area of this one circle, and then integrating it. So we're taking the area of a circle that's maybe up here, and we're finding the area below it, which requires pi r squared h. But here, we don't have just one cylinder. We have many cylinders. In fact, we could consider them to be infinitely many cylinders. So if we have a limit as h approaches 0, or if we consider the limit literally, if we have a bunch of cylinders with the 0 height, but they're perfect cylinders, then we should be able to add up all of them in order to get to the area of the shape. The volume of the shape. So we should sum the heights from x equals a to x equals b, because those are the bounding points of this curve that's going to be rotated around the y-axis, and it's of f of x. Sorry, of the individual volumes that each of these cylinders have. And then this should be able to give us the area of this curve rotated around the y-axis. But what is the volume? We know that they're cylinders, and then they should have a volume of pi r squared h. So then if we replace volume with pi r squared h, where volume equals pi r squared h, where h is the infinitesimally small change in x. In calculus, this is referred to as, I'm sure you know, dx. Then we can replace this v, instead of using pi r squared h, we can use pi, and then what is the radius? The radius is y, because it depends on the y value for each radius. Pi y squared dx. So the height is just a small change in x. The y is the function of x, because the value that the y takes as x increases is going to be the radius of the face of the cylinder that you're trying to do. And pi, which is the ratio of the circle's circumference to its diameter. So if we replace v with pi y squared dx, then we get the limit as h approaches 0 from x equals a to x equals b of pi y squared dx. And I'm sure you can find out already that this limit as h approaches 0 of the sum from x equals a to x equals b is the definition of the definite integral. So we can take all of this and get rid of it. We can replace it with the following: the integral from a to b, because it's x equals a and x equals b in sigma notation, of the pi y squared dx. And we said that y equals a function of x here, so we can replace y with f of x here, and pi is a constant, so it can be factored out of the integral. So then we get that the final formula is from a to b times pi of f of x squared dx. But what if the curve is not completely on the x-axis? What if we want to rotate it around something else? Well, if we move it up or if we move it down, then we can represent y equals f of x by plus L, right? Because if we move it up, then that'll be just a constant that's moving the whole function up. And right now, we have y equals f of x plus 0 because we're rotating it around the x-axis. So this f of x plus 0, the 0 cancels out, so it's just f of x. But if we wanted to be able to include that L, then we could rewrite the entire thing as the integral from a to b times pi of, I'll write this in text, of f of x minus L squared dx. And this is the volume of a solid of revolution that can be obtained by any curve.